Hi everyone, today we are starting chapter 10, which is a brand new chapter on conic sections. And our first conic that we're going to talk about is more with lines. So conic sections are formed whenever you slice either through or down along the side of the plane of two cones being stacked on top of each other. So it's like an hourglass figure that you see here. And there are four basic conic shapes that we're going to study over the next couple days. And some of you are familiar with some of these shapes, but you're going to start to look at them in a different way because there's different formulas that we can use for some of these shapes. So one shape would be the circle again. Another would be an ellipse. The third would be a parabola, and this is looking at a parabola a little bit different way. And then the fourth would be a hyperbola, which we talked about when we did rational functions. But again, looking at these without fractions, well, no, they will have fractions, but their equations are going to look a little different than what we've seen before. And then if you slice alongside of the two cones stacked up on top of each other, we could get what we call the degenerate conics, which are points, or we could get one line, or we could get two intersecting lines. So now that we know some trigonometry, we can have a couple more equations that deal with lines put into our math library here. So everybody knows that a line is going to intersect the x-axis in some place as long as it's not a horizontal line. A horizontal line never would intersect the x-axis unless it was the x-axis itself. But a line could be vertical and it would intersect then at a right angle. It could be an increasing line with positive slope and then it would intersect the x-axis with an acute angle, or it could be a decreasing line and it could intersect the x-axis with an obtuse angle. And this is called inclination. Inclination is the angle of which a line would intersect the x-axis, measured again in the counterclockwise direction. So inclination is directly related to the slope of the line, and it has to do with trigonometry again. If you would draw a right triangle, you can see that we know slope as rise over run, and the slope of this line would be the y over the x values. And so looking at that, the angle of inclination would be y over x, or tangent. So the slope of the line is directly related to the tangent of the angle of inclination. So you are asked to find the angle of inclination of these given lines. And these given lines, of course, we are going to want to find the slopes of the lines. Well, you could go through the work of ax plus by plus c equals 0 and solve for y. And if you solve for y, we would get everything over to one side of the equation. So the c would go over in the ax. And if we divide by b, we get this form of the equation. Or you could remember, and we've already talked about this a couple times throughout the year, that if you look at an equation of a line in standard form, the equation for slope is just negative a over b. So I can look at this equation and I know negative a over b, and I know that my slope is the opposite of 5 over a negative 1, and so the slope of this line is 5. So if they ask you for the inclination, you are going to set up the equation where the tangent of theta equals 5, and to find the inclination, which is theta, you would take the inverse tangent on your calculator. And I have my calculator set to degrees, and so when I find this angle of inclination, I get approximately 78.7 degrees. This should make sense to you. If you graph this line, you have a slope of 5, so if we were starting here, we would be going up 5 and over 1. This line would look like this, and yeah, this looks like it would be a pretty big angle, about 78.7 degrees. For the second one, we're going to get the slope, which is the opposite of a over b. You take the tangent of theta equals this. When you do the inverse tangent of negative 2/3 on your calculator gives you a reference angle, and it's going to be a negative reference angle from the x-axis. What that means is from the x-axis, it's saying, hey, I'm going to go down 33.7 degrees, and that's how I'm going to get this line. And that should make sense. Our line is decreasing. But we want angle of inclination. Angle of inclination goes from the x-axis in the counterclockwise direction. So to figure that out, you're going to want to add 180 degrees to this, and our angle of inclination would be 146.3. So if you get a negative angle of inclination, you just add 180 degrees. Here's using the same formula, but kind of asking you the question in reverse. This time they are telling you what theta is, and they want to know what the slope of this line would be. Well, you all should know what the tangent of 3 pi over 4, you know that that's -1. So the slope of that line is -1. And if I give you an angle of pi over 3, you know that the tangent of pi over 3 is equal to approximately square root of 3. And so square root of 3 would be the slope of the line. And the square root of 3, my calculator, is at about 1.73. So that would be approximately the slope of the line. Next set of formulas, this is finding the angle between two lines. So we saw on the conic that you could have an intersection of two lines going down the two sides of the cones. So now that we know some trigonometry, we have this angle between two lines formula that comes up. And if you look at this formula, the pattern of it should maybe remind you of something. It comes directly from the angle sum and difference identities with tangent. So that's where this comes from. All they're doing is they're taking the tangent of two angles, subtracting them, and they use the formula. And then the fact that we know that the tangent is equal to the slope, they substituted the slopes in here. So that's going to be our formula that we're going to use to find the angle between two lines. So in our next set of examples, they give us two lines, and we can easily, for line 1, figure out the slope of line 1 is the opposite of A over B. So that's -2. And for line 2, the slope is going to be the opposite of A over B, so that's going to be 1. And now we're going to take these formulas and we're going, or slopes, and we're going to put it into the formula to find the angle between. So that formula looks like this. And what we do is we take one slope minus the other slope divided by 1 plus the two slopes multiplied together. And on top here, we're going to get a 3, and on the bottom, we're going to get a -1, but we want the absolute value of all that. So on your calculator, you're going to be taking the inverse tangent of 3. And so when you solve, I got 71.6 degrees. Next one, line 1 slope, the opposite of A over B would be 2. Line 2 slope would be the opposite of A over B, which is -3/4. Can't do really much of that. We got the tangent of theta equals -3/4 minus 2 divided by 1 plus -3/4 times 2. So let's see, I'm going to look at 2. I'm going to get it as a common denominator. That would be 8 over 4. So this would be -11 over 4. And down here, I have 1 plus 3 over 2. Actually, that's a -3 over 2. So I'm taking 1 minus 1.5, so that's -1/2. So when I reciprocate and multiply, I get 22 over 4. Hang on a second. I have 22 over 7, and I'm not really sure where that's coming from. I think that's a mistake. I'm pretty sure my work here is right. Okay, so this is 22 over 4, which is 11 over 2. So I apologize if I made a mistake in my math. I'm hoping I'm right now. I'm going to take the inverse tangent 11 over 2. And so I get 79.7 degrees. So that should be the correct answer for this problem. Let me know in an email if I'm wrong. Okay, next example, distance between a point and a line. So this involves the distance formula, and it also involves the hypotenuse of a right triangle. So what you're going to do is you're going to take the equation of the line that you know, this would be like our line that we know the equation of, and we're going to find the distance between this point and this line. Shortest distance between 2 points is a straight line, and our straight line is going to make a perpendicular line with that. So what you do is you take the equation of the line, A, B, and C, and then you take the values of the point, x1 and y1, and substitute it in there, and then you divide it by the square root of a squared plus b squared, which is kind of like our Pythagorean theorem. So find the distance between the point and the line. Okay, so the distance between the point and the line, we need the equation of our line, which is 4x plus 3y, and we don't have a c, but we will sometimes, so it's really just plus 0, divided by the square root of a squared plus b squared. And down here, this is 16 plus 9, which is 25. So the square root of 25 is 5. And up here, I need to go back and put the points in 0 and 2. So this is 0, of course. This is 6 plus 0. This is 6. So the distance between the point and the line is 6 over 5, or about 1.2 units. Okay, I need to see how much time I have left. 4 minutes. Okay, I think that could be enough time. We have an application problem here where we need to graph a triangle. So we're going to use the points -3, 0, that's A, 0, 4, that's B, and 5, 1, 2, 3, 4, 5, 2, that's C. So here's our triangle, and they want us to find the equation of this triangle, or the area of this triangle, which we know as 1/2 the base times the height. Well, to find the base, we'll call this the base, we would use the distance formula. To find the height, we can use the formula we just used, which was the distance between a point and a line. So we're going to find, I'm going to find the base first. The base is pretty easy, of A and C. So I'm going to take the square root of A and C's points with the distance formula. So let's see, we have 5 minus a -3 squared plus 2 minus 0 squared. And so this is 8 squared, which is 64, and this is 2 squared, which is 4. So this is the square root of 68, and the square root of 68 is 2 square roots of 17. So that's pretty important. You want to remember that one. Now we got to go find the height. And in order to do that, the first thing we have to do is find the equation of line AC. So this takes us way back to Algebra 2, where you have to find the equation of line AC. So the first thing that you're going to want to do is find the slope of the line AC. So we're using A and we're using C. So the slope is going to be the difference in the Y values over the difference in the X values. So our slope is 1/4. And then you're going to use Y equals 1/4 X plus B. And you're going to put a point in. I'm going to choose A because it has a 0 in it. I always think it's easier to use a 0. And so here we get -3/4. So when we solve for B, that's 3/4. So our equation is Y equals 1/4 X plus 3/4. But we need standard form, which means we need everything on one side and we need no fractions. So I'm going to take everything over here and I'm going to get X minus 4Y plus 3 for my equation of that line. Now we're going to find the height. So we're going to use our distance that we just learned. We're going to take this equation, 1x minus 4y plus 3. We're going to divide it by the square root of a squared plus b squared. And we're going to put in this point b into x and y. So on top, I should get 13, and on the bottom, I should get the square root of 17. And I know you're probably eager to rationalize that, but don't. Because once you put it back into this formula to find the area, it's all going to work out for you. So the area is 1/2 the base. The base was 2 square roots of 17. And the height is 13 over the square root of 17. These cancel. Oh, the 2's cancel as well. So this is 13 units squared for the area of the triangle. This number should always work out to cancel. So don't rationalize your denominator. And if it doesn't work out to cancel, you made an error somewhere in your arithmetic. Okay, I got this in under 15 minutes. So you are going to work on your practice worksheet for 10-1, day 1. And you will have a quiz on sections 10-1 and 10-2. 10-2 has to do with parabolas later on coming up in the upcoming days. And then we will continue with the rest of our conics.